Chapter 6, Three-Phase Metering. When considering three-phase power generation, you can assume that it is made up of three single-phase generators connected together on one terminal. The generated voltage vectors, or phasors, are 120 degrees apart, rotating counterclockwise. The load can be connected in various configurations. In this case, we show a Y-connected load. Remember from a previous chapter that energy meters, regardless of their makeup, mechanical or electronic, are considered to be made up of meter elements. A potential coil or a voltage transducer and an A to D converter make up a half of the element of the meter, and a current coil or a current transducer plus an A to D converter make up the other half element of the meter. Together they make up a single element of a meter that can be used to measure power and energy consumption by a single phase load. Multi-element meters, regardless of whether they are mechanical or electronic, can be made up of two or three elements. Each element reads the average power, which is the RMS voltage times the RMS current times the cosine of the angle between them, which are then summed to give the arithmetic total reading of all of the elements. Let's look at a three-phase Y-connected load. Now that we have a simple model for a three-phase generator, we can replace it with a three-terminal generator. The generated voltage phasors are 120 degrees apart, and the Y-connected load is made up of three impedances, Z1, Z2, and Z3. In order to meter the load, we simply need to meter the individual power to each of the load impedances, then arithmetically sum the three meters. That is, we use 3 watt meters or a 3-element watt meter, each element measuring the phase to neutral voltage across the load and the current to each of the load, as in the diagram here, and then we sum the meters or the elements. As I said, we could use a 3-element meter to accomplish the same thing. Each element measures the phase to neutral voltage across the load and the current into the load. The digital processing unit then sums the total consumption. Before proceeding into the next set of metering type installations, especially for three-phase metering, we have to understand that utilities have installed or will be installing hundreds of thousands of these meters in their utility system, so that as a cost-saving measure, they try to keep the numbers of watt meters down, and certainly the cost of the watt meters down. And if you reduce the number of elements in a watt meter, certainly the cost will go down, because the cost will go up as you introduce more elements into the meter. And if you have fewer elements, then you have fewer CTs and PTs that have to be connected and the associated wiring. So all in all, there is a general trend, or has been a general trend, to reduce the amount of elements involved in a metering system. So what we're going to see in the next few installations is some approximations that are made that are acceptable from a billing standard, such that the cost will be kept down, and we'll be trying to reduce the number of watt meters, or certainly the number of elements in a watt meter, in metering three-phase systems. In a utility's three-phase system, often referred to as an infinite bus, because utilities tend to be very large and they're interconnected with each other, so that the infinite bus refers to the fact that the voltages, regardless of the loads, remain relatively unchanged. In other words, they are going to be equal and 120 degrees apart just about at all times. If we look at the voltages here, if we look at voltage V1, the vector would look something, or the phasor would look something like this. Then voltage V2, or V2 to neutral, would be 120 degrees lagging that voltage and look somewhat like this. And voltage 3 would look something like this. When the voltages are added together, because they're equal and 120 degrees apart, the vector sum, or phasor sum, of the voltages will add to 0. And for the next stage in metering a three-phase system, we'll use this identity where the voltages of a three-phase system will add to 0 in order to make reductions in the number of elements used in a meter. Let's go back to the three-phase metered load that we had up a few slides back, where we had a Y-connected load to the system with 3 watt meters measuring the power consumption of that Y-connected load. And we could say that the total power to the load is made up of the sum of watt meter 1, 2, and 3. So WT is equal to W1 plus W2 plus W3. And we know that the individual watt meters are made up of the product of the current and voltage in each of the phases. In other words, I1 V1 plus I2 V2 plus I3 V3 is equal to WT. We know that each element is reading the power average equation, which is the root mean square of the voltage times root mean square of the current times the cosine of the angle between them. We also know that because we're dealing with an infinite bus, that V1 plus V2 plus V3 is equal to 0, or we can say that V2 is equal to the quantity minus V1 minus V3. Then if we substitute V2 into our formula, we will get that I1 plus V1 plus I2 times the quantity minus V1 minus V3 plus I3 V3. All we've done is a mathematical substitution here, which is allowed. Now we can collect like terms in this equation, and we see that the formula tells us that we only need 2 watt meters to meter this system. And that is, we collect like terms in terms of V1 and V3. We see that the total power consumption by that load can be metered with 2 meters, one using the voltage of V1 and the current I1 minus I2, and the voltage of V3 and the current of I3 minus I2. And the total would be the sum of those 2 watt meters, or 2 elements that would be used to meter this Y-connected load. As I said, this formula tells us that we can use a 2-element watt meter. One element using voltage 1 and the sum of the currents I1 minus I2, and the other element using voltage V2 and the sum of the currents I3 minus I2. Let's see how this formula will apply to the industry standard 3407. The meter elements look like this, where element 1 is the bottom element of what's in our diagram, and element 2 is the top element of the diagram, as we see here. Using a 3CT and direct connected potentials. Instead of numbering, this standard uses letters, but the formula and relationships are the same. VAN is the potential as shown here in red going through element number 1. So it's the half element used for potential of element number 1. The current from line A is shown here, or I subscript A, and it goes through element number 1 in a positive manner. VCN is shown here, and it is the potential connection for element number 2. IC takes the current from the current transformer associated with the C phase, and it puts the current through element number 2 in a positive manner. Now IB, or the B phase current, goes through both elements, and it leaves the CT using, I'm associating it with a dark green, and you can see it goes up and through element number 2 backwards, which means it's being subtracted, or minus B, through element number 1. It comes back down, but doesn't return directly to the CT, but goes up and backwards through element number 2, which gives it a minus B for element number 2, which is shown in the light green here. After it goes through element number 2 backwards, it returns back to the CT and continues the circuit flow. If the current and voltage phasors are plotted, the resultant currents through each element are 60 degrees apart. The resultant voltages are 120 degrees apart. This 60 degree, 120 degree configuration is a standard for correct metering arrangement, and you'll see this in several of our metering arrangements. This setup, using this standard setup 3407, is what we would call non-Blondel compliant, and we'll explain that once we get into the Blondel section of this chapter, which is later on. The standard 3408 is the same type of metering, only this time we're using an S-base meter, which is a socket or plug-in type metering. The elements look like they're turned sideways, but this would be element number 1, and this would be element number 2. However, all the connections and CTs feeding the meter are the same as before for the A-base meter. Now, this type of metering, both with the socket base and the A-base meter using 3 CTs, and then manipulating the current so that you can subtract one from the other, is easy to do if you have current transformers, and they allow you to do this. If you did not have current transformers, in other words, if you had a direct connected watt meter, you could not connect the currents together. You couldn't make up I1 minus I2 because you would have to connect the primary phases together, which would short circuit them and it just wouldn't work. So in using this formula, how would you be able to use a 2-element meter or a less than a 3-element meter in order to meter this type of situation? Well, it's done using a 2.5-element meter, and you'll see that in the next slide. If we were to use a 2.5-element meter, it would allow us to sum the currents if they are directly connected. That is, there is no CTs. Now, you remember what a 2.5-element meter looks like. It has two current inputs, and they both share the potential coil. So you're allowed to take I1 through one of the coils, and you can pump I2 backwards through the other element, and then have it go through backwards through the other wattmeter and the other element as well, allowing us to use the same formula. WT is equal to W1 plus W3, which is V1, I1 minus I2, plus V3 times the quantity I3 minus I2. So wattmeter W1 would look like this, and it still gives us the average power. Wattmeter 3 still gives us the average power using the currents here in the formula. So again, we've satisfied the equation for calculating the total average power for this setup. However, this time we are using a 2.5-element meter. And again, and I'll state this and explain it later, this is a non-Blondel compliant setup. It is accurate enough for our purposes, but it is not a Blondel compliant setup. Let's look at our 3-phase 4-wire load again, and let's apply just a purely resistive load. This is just to make things look a little bit simpler. The I1 current phasor would look like this. The I2 phasor would lag I1 by 120 degrees and look like this. I3 current vector would lag I2 by 120 degrees and look like this. The I1 minus I2 current phasor would look like this. And the I3 minus I2 current phasor would look like this. In actual fact, the load does not have to be a Y configuration, since the calculations only deal with current and voltages to the load. This metering will work for any 3-phase 4-wire load. Again, if the current and voltage phasors are plotted together, the resultant currents through each element are at 60 degrees or 60 degrees apart, and the resultant voltages to those elements are 120 degrees apart. So this gives us the characteristic of accurate metering, which is usually plotted with voltages and currents at 120 and 60 degrees apart. If there is non-resistive elements, in other words, reactive elements such as inductance or capacitance in the circuit, there will be a shift of the currents either in a forward or reverse direction compared to the voltages. However, the currents will still be 60 degrees and the voltages will still be 120 degrees. Remember, this reduction in the number of watt meters, 2 instead of 3, was based on the fact that the voltages were balanced. This is purely a cost-saving measurement, and it is also a non-Blondel compliant setup. Metering any three-phase four-wire load with 3 watt meters or a 3-element watt meter is the best and most accurate, where the total power consumption, WT, is given by the sum of the individual watt meters or elements, W1 plus W2 plus W3. And element number 1 is fed with the A to neutral voltage times the A phase current. Element number 2 is fed with the B to neutral voltage times the B phase current. And element number 3 is fed with the C to neutral voltage times the C phase current. Using direct connected potentials to the meter and CTs and a 3-element meter, Measurement Canada Standard 3418 is a cost-effective way to meter a 3-phase 4-wire load using solid-state meters today. Solid-state meters, the price of solid-state meters has come down drastically with the development of them over time, so it makes sense to use a 3-element meter now instead of approximating the total with a 2-element meter or a 2.5-element meter. And with this setup, the voltages no longer need to be balanced. Metering a 3-phase 3-wire delta load, the delta load is made up of 3 individual loads connected phase to phase as shown in this slide. This time we are labeling the phases RWB, or red, white, and blue. To meter the load, we would use 3 watt meters or a 3-element watt meter. Each of the watt meters or elements are connected such that each watt meter or element measures the current through the load and the voltage drop across each load, red to white, white to blue, and blue to red voltage. The total power consumed is the arithmetic sum of the 3 watt meters. So as I said, the total load will be the summation of the individual watt meters, W1, W2, W3, or the individual elements of a 3-element watt meter. Substituting the voltage drop across each load and the current through the load for the W1, W2, W3, we get this equation. Remember that in a 3-phase load, the voltages will add, the voltage phasors will add to 0 as indicated here. If we would like to get the blue to red voltage in terms of the other 2 voltages, then we can write that the blue to red voltage is equal to the quantity minus voltage red to white minus the voltage white to blue. We can now go back to the equation above and substitute the term that we just found for the blue to red voltages, and we get this equation here. We can expand what's inside the brackets mathematically, and we end up with this equation. And we can further rearrange the terms, not doing anything magical other than mathematical manipulation, and we would end up collecting like terms. We would end up with the total power can be monitored by actually 2 watt meters or a 2-element meter if we're measuring the red to white voltage times the current through Z1 minus the current through Z3 plus the voltage white to blue and times the current through Z2 minus the current through Z3. So we haven't done much more than mathematical manipulation at this point, but we will recall that the current, the red phase current, is equal to IZ1 minus IZ3, which is Kirchhoff's current law, really. So we can substitute that in our equation. Similarly, by Kirchhoff's current law, minus IB is equal to IZ2 minus IZ3. So we can put I minus IB in our equation. So now our total equation, or our equation for the total power consumption, is given by the red to white voltage times the red phase current plus the white to blue voltage times minus the blue phase current. Now we can rewrite that equation and get rid of the negative sign, and you'll notice that we just changed the polarity of the white to blue voltage to be blue to white voltage, and we end up with an equation that is the total power consumed by this load is the red to white voltage times the red phase current plus the blue to white voltage times the blue phase current. This formula tells us that we only need 2 meters or one 2-element meter to measure the power consumption in a 3-phase 3-wire load. 1 meter element uses the red to white phase-to-phase voltage with the red phase current. The other meter or element uses the blue to white phase-to-phase voltage with the blue phase current. Since the measurement of power to the load only uses phase-to-phase voltages and phase currents, the load configuration doesn't matter as long as there is only 3 wires to the load, that is, no neutral. Looking at the voltage and current phasors, you see that we are using the red to white and white to blue voltages with the red and white phase currents. The resultant currents of each element are 120 degrees apart. The resultant voltages of each element are 60 degrees apart. This is the 60 degree, 120 degree configuration that is standard for correct metering arrangements. Let's look at a Measurements Canada Standard 3301, which is metering a 3-phase 3-wire load with a self-contained meter or directly connected. The first element sees the voltage A to B plus the A phase current. The second element will see the voltage C to B using the C phase current. And of course, the standard uses ABC for their 3 phases, whereas we developed the formula red, white, and blue, or RW and B, which matches up to what you see here. And metering any 3-phase 3-wire load using a self-contained or an S-base meter, such as Measurement Canada here uses 3302, the first element would be on the left, the second element would be on the right, and measuring the same quantities as an A-base meter, which we just looked at in the previous slide. And for a higher voltage, higher current circuit using PTs and CTs, such as Measurement Canada Standard 3311 shows here, the same equation holds true, where the first element takes in the voltage A to B with the red phase current, and the other element takes voltage C to B with the C phase current. And of course, you have to take into consideration the turns ratio of the CTs and PTs when you're coming out with your final answer. So far, we've been sampling excerpts from the Measurement Canada's standard connection diagrams and connections for metering systems, anything from a single phase to a three-phase system, 2-wire, 3-wire, 4-wire systems. They're all listed here on the Government of Canada website. They can be found at this location, and just about every metering system in Ontario and certainly Canada adheres to this standard so that we can continually refer to it and make sure that our connections are correct and are standard. The website has two sections: an Appendix A, which is 87 pages of electricity metering installations with color-coded connections, and you can leaf through them. We've gone through several of them here in this chapter. Appendix B is Measurement Canada's standard color codes for electrical metering installations. Now, these color codings don't necessarily, or they for sure don't affect the actual metering themselves, but what they do is they make it easier for those that are maintaining the system to understand how the wires are connected without having to go and separate out the bundles and have to reconnect or re-bundle them together after maintenance is done. The actual wired connections to a meter are also standardized, and most of the systems use what they call test blocks for the purposes of connecting and disconnecting the current and potentials to and from the meters. These test blocks are designed such that you can inject current or measure current and inject voltages or disconnect voltages by opening and closing switches. These test switches are also designed to take test plugs, which allow you to inject current or measure current in a metering circuit, and you can even do that without disconnecting the meter or the power source to the to and from the meter. Although it is recommended to remove the power and then do your connections and then reconnect the power. However, these plugs are made to bring out the power connections to your test equipment. And you can see here a side view of the test block where the switch is open, but the connection to the meter is still maintained through spring-loaded connections. And as the test plug is inserted, it makes connection with the bottom and the top of the plug, or the bottom and the top of the switch, and the current will then flow through our test plug connection. Once the flexi-test switches are mounted, they are wired to a standard, which is also found on the Measurement Canada standard connections. This figure shows a typical installation of a 2-element meter with the Hydro 1 Delta connection. Notice the indicated current flow through the CT and meter coil and the labeled currents at the test block. Also note that the neutral potential is shown having a solid or dummy fuse. This is the required connection. Tracing the potential current flow, you'll see that it flows from line A to neutral and from line C to neutral in the left and right elements. If the neutral potential link was a normal fuse and it opened, the potential coils would be placed in series, and potential EAC and ECA would be applied to the potential coils. This would definitely cause errors in the measurement. This figure shows a typical installation of a 2-element meter with a Schlumberger delta connection. And this figure shows a typical installation of a 2-element meter with a Measurement Canada delta connection. Now these connections basically read the same to the meter, or the meter reads the same current. It's just that the wiring on the test switches themselves are different. Blondell's theorem states that if energy is supplied to any system of conductors through n wires, that's n number of wires, the total power in the system is given by the algebraic sum of the readings of n wattmeters, so arranged that each of the n wires contains one current coil, the corresponding voltage coil being connected between that wire and some common point. If this common point is on one of the n wires, the measurement may be made by the use of n-1 wattmeters. Looking at our example of a 3-phase 4-wire system, the number of wires in that system is 4, and the common point is the neutral. So we can measure the total power to that load with n-1, or 3 wattmeters. Now this sounds like a pretty complex and long theorem. However, it can simply be stated that in a system of n wires, the number of wattmeters required to measure the total power is n-1, or the total power is measured with one less wattmeter than the number of wires. Certainly a lot better, or a lot easier to understand than the long paragraph that was just read. A single-phase 2-wire requires 1 wattmeter. A single-phase 3-wire system requires 2 wattmeters, or 2 elements. A 3-phase 3-wire system requires 2 wattmeters, or 2 elements. And a 3-phase 4-wire system requires 3 wattmeters, or a wattmeter with 3 elements. If a meter is wired correctly and the right number of metering components or elements are present for metering a system of n wires, then meters that meet the requirement of n-1 elements for n-wire service are said to be Blondell compliant. And it's usually accepted that there are no errors in this type of a metering system that are incurred by the connections. There may be errors due to the PTs or the CTs themselves, but as far as the connections are required, it should be reading 100% accurate. We did an example of 100% Blondell compliant metering in our example of a 3-element meter using Measurement Canada's standard 3418 as seen here. You can see that there are 4 wires and we are using 3 elements, which is, it meets the requirement of n-1 elements for n wires. When a metering system is non-compliant, that means the meters do not meet the requirement of n-1 elements for an n-wire service. Now, this doesn't mean that the metering is in error, because some of the assumptions that are made are within the accuracy rating that we're looking for. It just means that if the system was pushed, there is a possibility that we would land outside the metering accuracy that would be required. However, there's plenty of meters out there that are non-Blondell compliant, and they were basically put in the system because of economic reasons, as we stated before, where we could reduce the number of elements and reduce the number of PTs and CTs that are connected to the system in order to save money over the long run. Meters that do not have Blondel compliant to provide stability and accuracy of measurement, the reasons are you'd want to have fewer elements, as I said, and lower costs, especially true for electromechanical meters. There's an avoidance of interference between two elements driving a single disk in an induction meter. There would be fewer CTs and PTs, and in very high voltage systems, CTs and PTs can introduce a significant cost into the metering system. Of course, there's less wiring, and there's fewer things that can go wrong if there's fewer wires, as well as there's some savings in not buying the wire. Some of the assumptions that are made that are used, and we've looked at those already, some of the assumptions are that the voltages are balanced and equal and 120 degrees apart. Here are some examples of meters that are not Blondel compliant, and they can either be, in this case, going from left to right, there's 3 wires in this system, but they're only using 1 element to meter the system. And in the middle one, there's 4 wires, and they're only using 2 elements to meter the system. And in the case of Measurement Canada Standard 3407, they assume that the voltage vectors or phasors are equal and 120 degrees apart. So making that assumption doesn't introduce a great deal of inaccuracy into the metering system, as long as you can sum the currents, which they can do here in the case of using CTs. So they can get away with using a 2-element meter, and they do it quite often. And this ends chapter 6.